Our lesson today is to be able to take a look at relations and functions, and being able to tell the difference between a relation and a function. First, order pairs can be used to show inputs and outputs. Right? And we all know our order pairs contain an input, which is an x value, and output, which is a y value. A relation pairs inputs with outputs. A relation can be represented by ordered pairs or a mapping diagram. So here we have the relation represented by ordered pairs. We have ordered pairs of 0 and 1, 1 and 2, and 2 and 4. We have our mapping diagram showing the same relation. Mapping diagram maps a 0 to an input of 0 to an output of 1, an input of 1 to an output of 2, and an input of 2 to an output of 4. Notice that each one of these inputs has one output. So we can show the relation using ordered pairs, and we can show the relation using a mapping diagram. Alright, so here's an example of ordered pairs. The relation shown using the mapping diagram, but we're asked to list the ordered pairs based on the mapping diagram. So our first ordered pair would be 1, 3, because we have an input of 1 paired with an output of 3. Our next ordered pair would be 2, 6, because we have an input of 2 paired with an output of 6. Our next ordered pair would be 3, 9, and our final ordered pair would be 4, 12. Alright, if we look at our second example, we have an input of 0 paired with an output of 0. So 0, 0 would be our first ordered pair. Then we have an input of 2 paired with an output of 1. Now that same input of 2 is also paired with an output of -2. So 2, -2 would also be an ordered pair. Then we have an input of 4 paired with an output of -3. Alright, so if we're listing our ordered pairs from the mapping diagram, we just want to see make sure we pair the input with the output to create the ordered pair. Alright, let's try a couple more. Alright, we want to create the ordered pairs from the mapping diagram. Right, so we have an input of 0 paired with an output of 12. We next have an input of 2 paired with an output of 10. Next we have an input of 4 paired with an output of 8. Then we have an input of 6 paired with an output of 6. Right, so our ordered pairs would be 0, 12, 2, 10, 4, 8, and 6, 6. Our second mapping diagram, we have an input of 1 paired with an output of -1. That same input of 1 is also paired with an output of -2. We have an input of 2 paired with an output of -3. And we also have that same input of 2 paired with an output of -4. Alright, so we're just listing the ordered pairs based on the mapping diagram, but in each case it shows a relation. And a relation is simply an ordered pair, an input value paired with an output value. Alright, now if we continue, a relation is any set of ordered pairs. Relations can be represented as a table and as a graph as well. So we looked at the relation using a mapping diagram, but we can also show that relation as a table and as a graph. The domain of the relation is the set of x coordinates, or the input values. The range of the relation is the set of y coordinates, or output values. So when we look at our relation according to our ordered pairs, each one of these input values, or x values, is listed or in our domain. So -2, 1, 0, and 3 would be our domain values, or input values, or x values. Our range values, or y values, or output values would be 3, 2, -1, and 1. So if I list them as a table, We have a column for x values, a column for y values, and we simply list our ordered pairs in the x and y columns. Negative 2 comma 3, here's negative 2 for x, here's y for 3. 1 comma 2, here's 1 for x, 2 for y. 0, negative 1, 0 for x, negative 1 for y. 3 and 1, we have 3 for x, 1 for y. If we're graphing that relation, we would simply use our ordered pairs, and we would graph the ordered pairs on a coordinate plane. Alright, so let's continue. So here's another example. Here's the relation 2 comma 6, negative 4, negative 8, negative 3 and 6, 0, negative 4. We want to express that relation as a table and graph. State the domain and range. So first, we have our column for x and our column for y if we want to express the relation using a table. Our x values are on the left side of our table. 2, negative 4, negative 3 and 0 would be the input or x values or the domain values. Our y values, 6, negative 8, 6, and negative 4, they represent our outputs or our range values. If we graph those ordered pairs, right, they would look like this. Right, we have 2 comma 6, right, over 2 up 6. We have negative 8, negative 4, negative 8. There's negative 4, negative 8. We have negative 3 and 6. Here's negative 3 and 6. And 0, negative 4. Right. Here's something that's important. If a term in the domain or range appears more than once, only write it one time. In example 1, the value 6 appears twice in the range. Right? So if we're listing them, right, notice, let's go back up here, that in our output, our range values, 6 appears twice. When we list it here, we just write the 6 once. So our range values are negative 8, negative 4, and 6. There are our outputs or range values. Okay, let's try a couple on our own. Alright, we want to express this relation as a table. First we take our ordered pairs. Alright, I always like to do them in order from least to greatest, but you don't have to. So negative 5 is our least input value. Right, that's paired with an output of 2. My next input would be 1, paired with an output of 7. Then we have 3, paired with an output of negative 1. And we have 6, paired with an output of 2. Right, if we're graphing those ordered pairs, negative 5 comma 2, here's negative 5 in the x direction, up 2 in the y direction, put a point, 1 and 7 over 1, up 7, it's going to be up here, 3 and negative 1, over 3, down 1, it's going to be here. Then we have 6 comma 2, over 6, up 2, put a point. So here's our relation expressed as a table, and here we have our relation expressed on a graph. Okay, try the next example. Costs $3 per hour to work at Wildwood Amusement Park. Make a table of ordered pairs in which the x-coordinate represents the hours, right, or the domain values. The y-coordinate represents the total cost, right? Those are your outputs or range values. We have our domains are our inputs, range values are our outputs. Here, $3 for every hour. So 3 hours times 3 would be $9. The input would be the number of hours, the outputs would be the amount of money, right? The total cost. 4 times 3 is 12, 5 times 3 is 15, 6 times 3 is 18. Now, you could have started with 1, right? You could do 1, right? But they're asking us for 3, 4, 5, and 6 hours. So here's 3, 4, 5, and 6 hours, and the total cost for each. And there's our graph that represents that. Right. Let's do one on our own. All right. Movie rental store charges $3.95 per movie rental. Make a table of ordered pairs in which the x-coordinates represent the number of movies rented and the y-coordinate represents the total cost for 1, 2, 3, and 4 movies. All right, so we want the total cost for 1, 2, 3, and 4 movies. All right, our inputs represents the number of movies, right? So that's going to be our input. The movies going to go along our x-axis. Our outputs, the y values represents the total cost. Right? So that's going to be our outputs. Input movies, output costs. Here are our domain values, here are our range values. Well, the cost for one movie is $3.95. The cost for 2 movies would be what? 4 times 2 is 8. So that's going to be $7.90. 3 movies, 3 times 4 is 12, so that's going to be $11.85. And then 4 times 4 is 16, so that's going to be $15.80. All right. If we're graphing the ordered pairs, over 1 up $3.95, it's going to be here. Over 2, $7.90, going to be a little less than 8. It's going to be here. Then we have over 3 up to $11.85. Over 3, it's going to be a little less than 12. It's going to be here. And then we have 4 and $15.80 over 4, a little bit less than 16. And your points actually go in a straight path because there is a linear relationship there. All right. Next page. A relation that pairs each input with exactly one output is called a function, right? And the key with a function is for every input, there is exactly one output. So when we're determining whether a relation is a function, right, we look here, right? -9 is paired with 0, -2 paired with 5, 5 here, the output is 10, 12, the output is also 10. Because each input has exactly one output, the relation is a function. If we look here, right, -2 is paired with 4, right, -1 is paired with 3, right, so far, right, each of those inputs have exactly one output. But when we look at our input of 0, our input of 0 has 2 different outputs, right? 0, an input of 0 has an output of 5, an input of 0 also has an output of 6. And if we did that graphically, right, or let me just do that real quick graphically. If we're looking at that graphically, it would look something like this, right? Let's see, -2, -2 and 3, I should go 4 quadrants here, right? If we're looking at that graphically, -2 and 3, -2 and 3 is going to be something like that. -1 and 4 is going to be something like that. We have 0 and 5, right, would be like that. But then 0 and 6 is going to be something like that. And they'd be a little higher. Let's undo that. All right, because if that's 3, 4, 0 and 5 would be up here. 0, 6 would be up here. And then 1 and 6, right, it's going to be here. And then 2 and 7 would actually be someplace up here. But here's what I'm talking about, this being able to identify a function. We have something called the vertical line test. Right? And if we're looking at a function graphically, the vertical line test says if a relation is a function, then any vertical line drawn through a graph of the relation will always intersect the graph at exactly one point. Well, if I look at my vertical line test here, I notice that right here I have 1 point on the vertical line, here I have 1 point on the vertical line, but if I look here, I have 2 points on the vertical line, right? At 5 and 6 on the y-axis. Here I have 1 point on the vertical line, here I have 1 point on the vertical line. If at any point I have more than 1 point on that vertical line, it is not a function, right? So that would be an example of not a function, right? Because the input 0 has 2 outputs, 5 and 6, the relation is not a function. It fails the vertical line test. So I like using the vertical line test to show if a relation is a function, right? Because it's very easy to do. We just take our pencil and we just go back and forth along the line or the points and see if at any point are there 2 points on that vertical line. All right, so we continue. Consider the mapping diagram to the left. Determine whether the relation is a function. If we look at this first example, for every input there's exactly one output. So we know that that relation is a function, right? Because for each input there's exactly one output. Right? Describe the pattern of input and outputs when the input increases by 1, the output increases by 14. Right, and that would be a good description there. Right? If we're doing the on your own problems here, we want to determine if something's a function or not. If we look at this first example, right, I have two separate outputs for this one input, so that would be example of not a function. Right? It's not a function because negative 1/2 has two outputs. Alright, has two outputs. And it's not a function because 1/3 also has two outputs. Right? So that would be an example of not a function. Whereas here we see for every input exactly one output. Every input exactly one output. So this would be an example of a function. Alright? Now, last thing we're looking at is this idea of function notation. Now, function notation is very simple, right? Function notation, we'll see like f of x. We'll see the f here and an x in parentheses, right? Here it says f parentheses x is read the function of x. So I can read this as the function of x is equal to 15 times x, or I would read it as f of x, right? F of x. Its output, this is your output, right, or your range, or your y values, right? If I think of this as y is equal to 15 times x, right, that is the same idea, same function, same equation, same values, same inputs, same outputs. But if I write it using f of x with the f and parentheses x, then I'm using what's called function notation. So it's just another way of indicating that this is a function. Alright? The input x is any real number. This is your domain. Your domain are your input values, your output values are your y values, right? Or your f of x values. Right? Real simple. So if I want to find f of negative 3, that's the way I would read it. F of negative 3 is when f of x is 2 times the number x plus 1. F of x is equal to 2 times x plus 1. F of negative 3, I'm just replacing x with negative 3. So I'm evaluating the function when the input is negative 3. So 2 times negative 3 plus 1, 2 times negative 3 is negative 6. Negative 6 plus 1 is negative 5. So we're saying that this function, f of x is equal to 2x plus 1. F of negative 3 is the value of that function when the input's negative 3. So the value of that function when the input's negative 3 is going to be negative 5. Alright, so let's take a look at these two examples. Find the value of each function, right? So for part A, we have f of 2, right? F of 2 is going to be equal to 2 minus 4. So if f of x is equal to a number x minus 4, and we're replacing x with 2, it's going to be 2 minus 4, right? So f of 2 is going to be equal to 2 minus 4 is negative 2. So f of 2 equals negative 2 for part A. Part B, we have the function f of x is equal to 1/2 x plus 5. We want to evaluate that function when x is 11, when the input is 11. So f of, let's do part B. Right, so f of 11 is going to be equal to 1/2 of 11 plus 5. So f of 11 is equal to 1/2 of 11, which is 5.5, plus 5. So f of 11 is going to be equal to, what's that, 10.5? So f of 11 is equal to 10.5. Right? So it's just more vocabulary that you're becoming familiar with. Right? You have your domain or your inputs, your range or your outputs. We have function notation. We read it as f of x. Right? You can organize the input, the rule, and the output into a function table. The variable for the domain is called the independent variable because it can be any number. The variable for the range is called the dependent variable because it depends on the domain or input values. So here's an example. Here's our function. F of x is equal to number x plus 5. The domain values or input values, right, are independent variables. Negative 2, negative 1, 0, and 1. The outputs depend on the inputs. So these are your dependent variables, or your range. Your range values, or your y values, or your f of x values are 3, 4, 5, and 6. Alright, so we'll just do a couple of those and then we're all finished. Alright, first example, f of 7, if the function rule is f of x is equal to 5x, so f of 7 is going to be equal to 5 times 7. F of 7 is going to be equal to 35. F of 9, when f of x is equal to x plus 13, so f of 9 is going to be equal to 9 plus 13, right? And 9 plus 13 is 22, so f of 9 is going to be equal to 22. Right? F of 4, if f of x is equal to 3 times the number x minus 1, so that's going to be f of 4 is going to be equal to 3 times 4 minus 1. Right? So f of 4 is going to be equal to 12 minus 1. F of 4 is going to be equal to 11. Alright? We'll do a couple of these function tables and be finished. Right? It says choose 4 values for x to make a function table for each function. Then state the domain and range of the function. Okay? So let's use inputs of 1, 2, 3, and 4, right? But that is your independent variable because those values can be any value. If we choose our inputs or our domain values as 1, 2, 3, and 4, right, we evaluate the function. 6 times 1 minus 4, 6 times 2 minus 4, 6 times 3 minus 4, 6 times 4 minus 4. 6 minus 4 is 2. So when the input is 1, the output is 2. 6 times 2 is 12. 12 minus 4 is going to be 8. 6 times 3 is 18. 18 minus 4 is 14. And then 6 times 4 is 24. Minus 4 is 20. So when our input is 1 with this function, our output's 2. When the input's 2, our output is 8. When the input's 3, the output's 14. When the input's 4, the output's 20. They want us to state the domain and range, right? So the domain, right? The domain is simply, right? We write it this way using a little bracket. Is what? 1, 2, 3, and 4, right? That's the domain values. The range values, all right? They're your outputs. So it's going to be 2, 8, 14, and 20. Right? Those are your range values. Right? Pretty simple. Next example. Right? We can choose anything we want for our independent variables or our input values or the domain values. Right? All those vocabulary mean the same. So let's do 0, 1, 2, and 3 this time. So it's going to be 5 minus 2 times 0. It's going to be 5 minus 2 times 1. 5 minus 2 times 2, and 5 minus 2 times 3. All right. 2 times 0 is 0. 5 minus 0 is 5. So when the input's 0, the output's 5. 2 times 1 is 2. 5 minus 2 is 3. 2 times 2 is 4. 5 minus 4 is 1. 2 times 3 is 6. 5 minus 6 is negative 1. All right. So we have our domain values, right? The domain, simply write it as, what do we have? 0, 1, 2, and 3 for the domain. And our range values, right? Range are going to be 5, 3, 1, and negative 1, right? For the range. All right. Next example, I don't know. Choose different inputs. Let's do, I don't know. Let's do -4, -3, -2, -1, right? Because we can use anything we want for our inputs. That's why they're called the independent variable, right? They can exist by themselves. So 7 plus 3 times -4. Then we have 7 plus 3 times -3. 7 plus 3 times -2, and we have 7 plus 3 times -1. 3 times negative 4 is negative 12. 7 plus negative 12 is negative 5. 3 times negative 3 is negative 9. 7 plus negative 9 is going to be negative 2. 3 times negative 2 is negative 6. 7 and negative 6 should be positive 1. And then we have 3 times negative 1 is negative 3. 7 and negative 3 should be positive 4. So our domain values are negative 4, negative 3, negative 2, and negative 1. Our range values are going to be, what do we have? Negative 5, negative 2, 1, and 4 for the range. Alright? And the last problem we're going to do, in a recent 82-game season, Dwight Howard of the Orlando Magic averaged 20.7 points per game. His approximate total points scored, P of G, that's the way we'd read that, is a function of the number of games he played, right? So the total points, if he played one game, and he's averaging 20.7 points, that'd be 20.7 points for one game. 2 games, 20.7 times 2. 3 games, 20.7 times 3, and so on. Identify the independent variables. Your independent variables, they are your inputs, right? Those are your games, right? So that's going to be your games, or your G. Your dependent variable, right, is your P of G, all right, or your dependent variable is going to be what? Total points, right? Total points, however you want to describe that. So the number of games are your inputs or independent variable, or your domain values. Your dependent variables or your outputs or your range values are going to be your total points. What values of the domain or range make sense for this situation? Well, if it's an 82-game season, your domain or inputs should be, let's see, your domain should be anywhere from 0 to 82, or if you want to do 1 to 82, right? Those would be your domain values, right? The 82-game season should be 0 to 82 or 1 to 82. Your range, right? Your range would simply be, right, your total points. Right, your total points would be your range. Write a function to represent the total points scored, right? Well, P of G, right, that's going to be equal to the 20.7 points, right, per game. So if we want to know the total points scored in 9 games, P of G, right, that's sloppy G, P of G is going to be equal to 20.7 times 9, and 20.7 times 9 is 186.3, I believe. It's going to be 186.3 points. All right. So I know that we went through a lot of vocabulary today. You know, as long as you understand that relations are sets of ordered pairs, functions are specific types of relations where every input has exactly one output. Your inputs are also your x values, which are also your domain values, which are also your independent variables. Your outputs, which are your y values, are also your range values, which are also your dependent variables. All right, we can use the vertical line test to help us identify functions as well, using that vertical line and running it across the plotted points on a coordinate plane. And if any 2 points lie on that line, it is not a function. All right, hopefully that's been helpful, and we'll see you soon.